So first of all, to the organizers and the program chairs, I feel grateful for your endeavors to make this conference possible. I am happy to have been a part, no matter how humble, of this development. Here is the points I'm going to deal with more detail later on. One is that I think deserves a little celebration, which is the experiments of Sternger-Lach in 1922. Here, the picture on top, you have the prediction of where, let's say, the silver atoms fall when there is no magnetic field. Image B is the prediction of Maxwell's theory. The image C is the prediction of the so-called old quantum theory. There were 3 values. And finally, what they found in this experiment is that they actually got two values, plus mu0 and minus mu0. Actually, there is a nice analysis here in paper number 3, wrong theory, right experiment. I think it's very interesting to read. I'm not going into that now, but say that Otto Stern emigrated to the United States in 1933, you know why, and was awarded the 1943 Nobel Prize in Physics for his contribution to the development of the molecular ray method and his discovery of the magnetic moment of the proton, not for the Sternger-Lach experiment. In his Nobel lecture, he said, "The classical theory predicts that the atomic magnets assume all possible directions with respect to the direction of the magnetic field. On the other hand, the quantum theory predicts," his meaning, the lecture was much later, he is already meaning the new quantum theory, predicts that we shall find only 2 directions, parallel and anti-parallel to the field. And in parentheses, he says, "New theory, the old one gave also the direction perpendicular to the field." So this, I think, was a big surprise, and it had very many consequences, most of them developed under the roof of geometric algebra. I would like also to celebrate a little bit the fact that we are celebrating 500 years, almost exactly, of the return by Juan Sebastian Elcano, of the only ship surviving the expedition of Fernão de Magalhães around the Earth. He made the design, he made the planning, but he was killed in a skirmish in an island in the Philippine Islands. And Juan Sebastian Elcano returned following a route that had been explored before by Magallanes, back and forth from what we call the Moluccan Islands now. See, life is hard, but at this travel, there were 239 sailors, 5 ships, and returned 18 people, 18 sailors, and 1 ship. I think that this book by Burstein, The Discoverers, has a nice quotation, which is: "The most promising words ever written on the maps of human knowledge are terra incognita." In fact, it is really amazing that these people could navigate around the Earth without not knowing the stellar disposition, the constellations of the southern hemisphere, and so on. Now, I said that this is the roof that has, under which most interesting developments have been happening in studying the spinor and spinors. Now, my presentation of geometric algebra will be very fast, and it's like a student presentation. besides setting notations and conventions, I think that I would like to say that I look at three main aspects that, for me, it is important that they are harmonized. One, the applicability side has unfolded in the last 100 years. And as I said, for the most part, it has been based on real geometric algebras. Second, the computational side by highlighting the structural and algorithmic relationships between notions. And third, the mathematical side by pointing out the relevant mathematical structures involved and how they fit together. Although geometric algebra will keep being central in most applications, it seems wise to allow for other possible inquiries, scalar fields other than the real numbers, as for instance finite fields for applications connected with discrete mathematics, or the rational number field for infinite precision arithmetic and symbolic numeric processing, and why not, this is a little bit wild perhaps, a p-adic field for more esoteric applications in mathematical physics. I quote a survey on this for the last 30 years on these developments. My point of view is that the geometric algebra formalism and its geometric semantics form a perfect match in familiar contexts. After all, this is the main reason why geometric algebra is so valuable. In less familiar grounds, the validity of the algebraic formalism is the only sure asset, and it is this asset that confers geometric intuitions to the studied objects and their relations. As I said, now I'll do a quick overview of geometric algebra for notations and conventions. And I have to say that it will be fast because of the constraints on time. It has been designed, the presentation, so that anybody interested in it can really read it almost as if it were paper, because there are notes that can be accessed by this N. At the end of every note, there is a comeback button, which is a P for returning to the page. And I hope that is useful at least to somebody. Now, the geometric algebra, for me, I will denote it by G. It depends on the quadratic form on a vector space V. The dimension of the vector space I'll denote by N. If we are in the real case, I will use the usual notation for RST for the signature, R positive for an orthonormal basis, R positive, S negative, and T null vectors. And in the case that there is no T, I write simply GRS. And if if S is 0, I'll denote it by GN. The polarized form of eta is this formula, and using it, you can have a multi definition of eta as eta of VB returns eta of V. Now, the main things that that should be stressed are that the great decomposition. So you have n pieces from 0 to n plus 1 pieces from 0 to n with the usual terminology. The piece G upper K, it has grade K. The decomposition of an element of G, a multivector, let's say, in pieces can be denoted like that. Many people denote it with this notation, and the scalar part with this notation. And of course, then you have the dimension of Gk is n choose k. The dimension of G is 2 to the n. G0 is the scalar field, and G1 are the vectors. Pseudoscalars are the elements of Gn because it has dimension 1. And then we have the wedge or outer product with all the properties we know. The most important of them is that if if we have vectors v1, vk, the wedge product is an element of g upper k, and that this element is non-zero, even only if the vectors are linearly independent. And in this case, this is said to be a K-blade. And of course, the wedge product has all the properties. You can construct bases by using this symbolism. You take multi-indices, say of grade K, and then you can multiply with the wedge product. You get a number precisely n over k, n choose k elements, and this is a basis of gk. It's easy to construct the product, or the wedge product of this basis, and therefore you have a computational tool to work with it. The inner product, first of all, I would like to say that it's bilinear, G-valued, and non-commutative. This, I put a footnote here because if it extends the inner product of vectors, the fact that it's not commutative seems to some people, or some people are bewildered by this usage of the dot. Well, one can get accustomed to that instead of relying on a left contraction and a right contraction. It has these properties. I would like to stress that it is necessary for coherence that a scalar dot a multivector, or a multivector dot a scalar should be zero, and then the usual properties with which the commutation rule, for example, in the case of one vector, you get this, and the recursive way of computing. The relation to the quadratic form is as follows. It's seen later on that eta of x and x prime, if they are homogeneous of grade k and grade j, then this value of eta x prime can be computed, is related to the inner product with this sign. This sign actually is the sign of the k choose 2, but it can be simplified for computations as the integer part of k divided by 2 that I denote with this form. This is the Python notation for this quotient. On the other hand, eta makes grade k and grade j, if j is different from k, orthogonal, which does not happen for the inner product. And another piece of notation is that if you have a basis, we say eta of ei, which was defined before, to denote the product of the corresponding values for the basis. It's easy to construct a table of inner products which can be used for computational problems. The geometric product is unital, bilinear, and associative, and it depends. It's constructed on this approach, of course, using the contraction rule. And I find it necessary to use a transference rule that says that the geometric product of V times, let's say, a K blade is the K plus 1 blade wedge product if the V is orthogonal to any one of the factors in this product. Then out of that, you get all the typical relations, like the recursive formulas for computing vector geometric product of multivector, or the other way around. This is the famous decomposition. You can get a formula for computing the products of two elements in the basis. Again, this is computationally interesting. It is easy to see that any blade can be written as the wedge of pairwise orthogonal vectors. The previous slide implies that any blade can be expressed as a geometric product of pairwise orthogonal vectors instead of wedge product. Now, there are a number of formal rules like the parity involution. It is consistent with a wedge, the inner and the geometric product. You define the event subalgebra as usual. You have the reverse involution. It is related in the case of homogeneous element with this formula. Again, it is compatible with the wedge, the inner, and the geometric product. And you have the Clifford involution, which is composing the reverse and the parity, and you get, it's denoted usually as X bar, and you get this formula here. Again, then you reconstruct, and this is part of the marvel of geometric algebra. You can reconstruct the wedge product from the geometric product and also the inner product, and you can find the components of a geometric product. The least possible one is the inner product, and the higher one is the wedge. Here, it has to be, this is true if j and k are greater than 0. Otherwise, the recursive formulas would fail. And finally, the formula that gives the eta in terms of the geometric product is simply the reverse x times x prime, take the scalar part, or the other way around. And in case you can ensure that the product is already a scalar, then it simplifies, like in this case here. And finally, you get that eta of x is not x squared, but it has a sign that depends on this formula. Well, the pseudoscalars is just to say that if you take an orthonormal basis and you do the wedge product, you can get only two possible values, depending on the orientation of the orthonormal basis. And this, by all that we said, we have what is the eta, is -1 to the s, is the number of negative terms. And you can have also the Hodge duality, and perhaps this formula here, that the square depends on n and s, according to this formula. The pseudoscalar commutes with vectors if n is odd, because then this is even, and is an important fact. And finally, the Hodge dualities are isometries. This, I think, is an important point. If the eta of I is 1, or anti-isometries if eta of I is -1. Now, this has to be systematized as follows. I squared, we said that is this expression. If we look at s minus r mod 8, then you get I squared is 1 for nu equals 0.347, or 0.3 mod 4, or -1 for nu 1.256, which is 1.2 mod 4. I will need this for some sort of a spinors. In fact, from nu defined as s minus r minus 8, one can find that this sign here, the sign here, it turns out to be nu plus 1 slash 2. Since n is congruent to n mod 2, we find that I is central even only if nu is odd. Okay, which is what we have here. Now, spinors and their kinds, there are mainly, in my view, mainly two species. One is as members of the spin group, or the pin group, or the rotor groups. This could be called, at least allow me to say it this way today, active spinors. And then there is another kind, which is the one most used by physicists, which are elements of a representation space, of a spinorial representation space. And for today, we could call them passive spinors or physicist spinors. My message in this part is just telling you how this goes. I think that it is important to remember that you can take the reflection across the hyperplane orthogonal to a non-null vector U by the formula that it was refreshed in former talks like Leo Dorst, that if you take...
Sebastian, just want to let you know you have about 5 more minutes.
Excuse me?
You have about 5 more minutes.
5 more minutes?
Yeah.
Well, I started at 11 minutes, so I should have at least 6 or 7 more minutes.
We can give you 6.
Okay. So this gives rise to the spin groups, for, let's say. In the case of real, they are products of unit vectors, and these are important because they give the orthogonal transformations by the sandwich product, and these are one sort of spinors. Of course, you have to also distinguish the rotors, which are in some sense primordial in all this theory. Now, when you do a representation of the geometric algebra G, in particular, it induces a representation of the spinorial group, and the elements of the space of the representation are called spinors if the representation is spinorial, which means that the -1 does not go to the identity. This is not what happens with the vector representation of the spinors, because the spin, the -1 and 1 go to 1, and therefore -1 gives the identity. You may say that vectors are not spinors. And among the spinorial representations, it takes a very important part, the minimal ideals of the geometric algebra, because then the representation is for free. It's just multiplying by the elements of the algebra. This, I would like to say much more about that, but it's impossible. Now, the classifications of the geometric algebra were I think that Chris Doran reviewed it. You have here this table that for nu equal from 0 to 7, you have a fundamental form, reals, complex, quaternions, double quaternions, quaternions, complex, real, and double real. There are only 5 different. They have a dimension over R, which is this one, always a power of 2. The exponent is this one. And then you can take the values of G bar nu, which is 0 nu, and you get, you find these formulas in matrix form. H2, for example, means 2 by 2 matrices over the complex, over the Hamilton quaternions, or I prefer to say geometric quaternions. And the G nu, which is nu 0, is except the dimension of the matrices going the other way around in this row. This can be programmed. This table is in a slanted way, the triangle that's shown by Chris Doran. And I think this is an interesting way of summarizing the classification, because I call it the horologion. It is not mine. It has been developed by many people. But this, you can read, computing the nu, you can read the form of the algebra at the tip of the arrow. You can read the form of the even algebra at the tail of the arrow, and you can find the dimensions of the basic representations of the algebra by using these m's, which are defined in the way I said before. Now, this table gives these basic the basic forms for the spinorial, the passive spinors, and then 1 century of spinors. I only can say that I have provided among the hundreds of references, a few of them that I think they are more representative. And I would like to stress that we are living in the Hestenes era. Let me call it this way. With the Gospel of the Space-Time Algebra of 1966, with the second edition of 2015. I would like to quote the preface, the foreword by Anthony Lazenby in this new edition, and the prodigious, I think it's a prodigious preface by Hestenes after 50 years. And you can find all the history in the Genius of Geometric Algebra, a personal perspective. I'd like to say that there is an excursus here, which is 3 very interesting papers that are not directly related to geometric algebra. One is this paper on James, papers on explaining or giving a review of this book here, the one down here on the right, the papers on probability statistics and statistical physics. Then there is this paper that, unfortunately, I think many more people should pay attention to and follow up, and other papers written later on by other people, which is How the Brain Works, the Next Great Scientific Revolution. This is a very far-seeing paper written in 1987. And then in an interview about his life and achievements. In any case, you have here this book. And this Hestenes era began with this big bang of, this big bang of Hestenes, and there have been many books and many others that cannot be put here. In this note, you can find the details, in this note here, the details of the authors. And then I just refer a short sample of other recent works that are related to spinors that because of the time, I think that I will just leave for you. And as I look, I think that we should advance in the application of geometric algebra and geometric calculus to deep learning models. In the reference 32, which is a collection, there are very many references. This was published in 2022, so it's relatively up to date. I think we might want to revisit infinity. There are several papers, several books about the spinors in Hilbert space and infinite Clifford algebras. I think that the exploration of discrete mathematics applications of geometric algebra, say over the integers or over the rational numbers, over finite fields. There is the line of exploring physics applications of geometric algebra over a p-adic field. And this last one, I call it a light dream. This is a quotation of a little paper I wrote for homaging 2 people that were retiring. And it was based on some work of David Hestenes a little earlier than what he told us today. I said that geometric algebra as a base for an inquiry aimed to understand in that formal reason knotted vortex electromagnetic solutions, this is already known, and to seek analogous solutions for the Dirac equation following seminal work of David Hestenes. Thank you, and thanks the organizer again, and program chairs.